So this is the second video in a series where we're looking at these 5¼ inch 360K floppy drives that I purchased on eBay in this dual drive case. It had these power supply / pass-throughs in the back of the case. If you remember in the previous video, there were large orange capacitors, 3 of them on each one of these boards that had failed. They had spit their guts out, honestly, but it didn't like make a mess on the board. It was just kind of a nasty black-white goo that had burst out of the caps. They were 2000 microfarad 40 volt, which is kind of an odd value. And the 40 volts is pretty high. So my question becomes, what is the output of the transformer here? What kind of voltage is it producing? And they really need to be 40 volt caps. In my stock, I have a bunch of these 2200 microfarad 25 volt. I've got more than enough to replace all 6 of those with those. I've got 5 of these 3300 microfarad 25 volt again, but for the radial, or these axial, the axial lead caps like this, I don't have a whole lot of selection. So what I want to know is what the voltage out of the transformer is. So the unit's plugged in, the fuse looks good, so let's just go ahead and measure the voltage coming out of the transformer. So the switch is off, it is plugged into the wall, the supply's on AC. So that's across both the outside edges of the transformer. So this is the maximum AC voltage the power supply can generate, and the fuse definitely is good. 14.5 volts. So I would expect to see this center tap around 7¼ volts, half of that, if this is a 50% center tap. 7¼ volts. And this is going to be 7¼ as well, looking in from the other side. So we've got, what was the maximum here? It was 14.5, I believe, is what we determined. It's coming through 14.5 volts here. So through a diode bridge and smooth on a capacitor, a general rule of thumb is you can take the AC voltage and multiply it by about 1.4 and get approximately the DC voltage you're going to see. And I have a working calculator here. I think the batteries are dead in my TI-30. Yeah, that's a shame the battery's gone. But, so this is, let's call it 15. 15 times 1.4, well, times 1.5 would be 15 plus 7.5 would be 22.5. That's approaching the max rating of these caps. It's most likely going to be less than that. For the 5 volt side, it's going to be, the 7¼ plus 50, it's going to be around 10 volts. So that's absolutely fine on that side. Really, I guess the only way to really know what this is going to look like is to put some of these in the end and measure the voltage across them and see what we get. So let's go ahead and do that. Power's off, meter's off. So let's look at bending some leads up here. So one of the things that's happened with capacitors, I want to bend this such that you can read the labels. Over the years, as the same ratings of caps get smaller and smaller, just because the technology gets better and better. So, oh, come on. Sit in there. I want to bend that side about there. So the idea is he will sit there. We'll just bend 2 more to look like this. And we'll power up one of the boards with them soldered in and see what we get. So I'll probably I'll create a service tag for these to put in about what they were when they were replaced, etc. So 2 of them are going to go this way. And this is a little bit more capacitance. We've gone from 2000 to 2200 microfarads. 2200 being a much more normal or typical value. 2,000 to me is just kind of an odd value as I think about it. Where's the cleaning thing? We'll hit these from the front first, just to hold them in place. And then there was one more. Negative down, positive up in there. Flare his leads a bit. Do the same thing. I'm just going to solder him from the top first, then we'll flip the board over and solder from underneath. Pretty stock standard linear power supply here. Nothing special about this at all. Transformer, bridge rectifier, capacitors, linear voltage regulator. In this case, 7805, 7812. So there's no magic here. There's no switching. This should produce a nice, pure, clean DC voltage. Yeah, I'm guessing had I wanted to attempt to swap in or to purchase actual 2000 microfarad 40 volt caps, they would be pretty much a specialty cap at this point and probably would have been very expensive. I tried to go to Jameco this morning to order some stuff and their website was down. And it was odd. There was definitely a page that there was an issue. Just makes me wonder what's happened to them. That, you know, it's always spooky when I see a website offline that I don't expect to be offline. So I know that these were in parallel. These were in parallel. This is ground, but I don't think yeah, that was the caps charging, so that's not in parallel. We've got these little 100 microfarad 35 volters sitting down here that I'm not exactly sure why they're there in this, but they are. Let's because all the rails have a common ground, we'll go to volts. We have a common ground. Nobody should explode here, but what kind of voltage am I working these caps at? Why are they not being worked at all? Oh, I'm on AC voltage, that's why. DC volts. So 18 volts, around what I was guessing. So I've got, what, 6.5 volts of headroom here below the rating. So I'm not too worried about that. And I expect this one to be closer to like 10, 9.2. So this cap's not being worked hard at all. And these are, 18.4, 20, that's what, 7.5 volts. These are 33% under their maximum working voltage. They should be absolutely fine. So I have no problem with those as a substitution. We should be seeing, I believe, plus 5 here on the red lead. That's from the 7805. Plus 12. Plus 11.95. Those two regulators are probably fine. Let's go ahead and turn the power off. Those caps are probably still charged. Let's get this unhooked. There's no bleeder resistors. It's not like there's high voltage on here, but there's no load. The drives aren't connected, and so these may or may not be holding a charge. Yeah, you can see him discharging here. This guy's probably going to be in the same space, slowly discharging. This is parallel to it. So we can see, they're bleeding off over time, as they will. So, that's not an unexpected behavior. That's why you see bleeder resistors when there's higher voltages, dangerous voltages. in things like in the switching power supply, that main filter cap that might have 200 or 400 volts across it. A good design will have a bleeder resistor. I could imagine this unit got pretty warm inside to heat off the drives. It was probably on 24/7 for who knows how long. Could have been years. Just really don't know. So, and eventually, like I said, I'm guessing it was CPM with a PIP command. There's other OSs that use PIP as well. PIP, Peripheral Interchange Program. It's used to move files between things. You can PIP a file to a printer or a console, or typically you're between drives as is being done. So positives are to positive, positives to positive. The negatives are all straight back. I'll double check over here. Positive, negative, negatives and positives. Everybody there looks happy. Thus, I'm happy. In this case, we'll look at this side. That's a common ground point. We'll turn on the AC voltage. We should be getting around that same 18 volts here. These are in parallel. Of course, it's going to be the same. I think this was, what, 9.5 or 8.5? Yeah, 9.1. That 9.1 is plenty of overhead for the 7805 regulator to kick in and regulate. 7805 requires 2 or 2.5 volts. It depends on the manufacturing of the regulator. The manufacturer of the particular regulator you have will have a specification for the minimum overhead voltage required to get decent regulation. But that 7805 seeing 9.1 volts coming in, as long as it's a good regulator, any 7805 should work fine in that situation. That should be a +5 regulated output. That should be a +12 regulated output. On this +5, we see 5.09. I don't remember what we saw over here. It's a different regulator. 5.07. Again, these boards are independent. They just happen to have the AC incoming power split here. It's an interesting design decision by whoever designed this. It's very flexible. If you had a single drive unit, you'd use one of these boards. If you had a dual drive unit, you'd use 2. If you had a 4 drive unit, you'd use 4. It creates an interesting cabling situation because the drive-to-drive cabling is, of course, going to be out of the back of the unit. But that's not honestly a problem. I don't know. I'm happy with this at this point. Trying to decide if there's any reason to load test this, and I don't know that there is. I'm just going to leave it on for a while with no real load. Nothing should get hot. There should be very little current being drawn through the regulators, so they're not generating a lot of heat. Everything should stay nice and cool. This should be safe to just kind of leave here in this state and and call this video done. I don't see a need to go any further at this point. I hope you learned something. If you got this far in the video, as always, I appreciate it. I hope to see you in a future video.